Okay, so again, I want to thank the people who did the work, many past and present group members. A lot of the work are done by a previous graduate student, Jiting Lee, um, in collaboration with Shigeru Mimiya, electrochemist, and also Professor Li Lei in Pitt Chemical Engineering. In his group, two students in particular made a very significant contribution in the early days of the work, Andrew Cosbell and Yunjing Wang. Okay, so I want to start from what was left yesterday. And yesterday I made the case, hopefully I convinced you that the wettability of carbon materials and many 2D materials are being unintentionally modified by environmental factors. And simply by exposing your 2D material and graphitic materials in general, in particular, the wettability has been significantly changed, as short as an hour or, an hour of air exposure. So again, taking a very broad look at how people are being using carbon material, energy storage would require a good understanding of the double layer structure that is related to the surface. Electrochemistry involves electron transfer between electrodes and solution redox couple. Again, that involves some kind of interfacial process. Composite materials involves adhesion. Lubrication involves friction and sliding action, and that again involves some kind of interfacial process. Certainly catalysis, separation, they heavily involve absorption, and those are directly related to surface energy. So if you take this broad look, you may come to the suspicion that if the wettability of graphitic materials has been unknowingly modified by the environment and has escaped people's attention in the past 70 years or so. We're talking about 1940 all the way to 2010-ish. So 70 years of research, people have been measuring contaminated carbon by atmosphere, and they didn't know that. Their other properties are being subject to the same kind of unknowing contamination. So we took a very critical look within this very broad range of questions. So in case you missed my lecture yesterday, the basic thesis here is that the wettability measured in the literature on graphitic surface, which usually produce a hydrophobic behavior, that is actually incorrect. And the reality is atmospheric hydrocarbon absorb onto the surface, and that produce this rapid increase in the hydrophobicity of the surface, and that is the origin. And the origin of that is the atmospheric hydrocarbon absorption. So I didn't get a chance to discuss this, but even beyond 2D material, so yesterday I talked about all this contamination on 2D material, but even beyond 2D material, this behavior happens on pretty much everything. Okay, and I'm going to show two examples. One is the TiO2. There's this very well-known wetting transition reported back in 1997, where they showed that TiO2 surface can switch between a hydrophilic and a hydrophobic state. Exposure of the TiO2 to UV light make it hydrophilic, and if you leave it in the dark, it becomes hydrophobic. This is a very interesting behavior, certainly, and the authors proposed that oxygen absorption was the mechanism, and UV excitation kicks off surface absorbed oxygen. But later it was found that there's no oxygen absorption on TiO2. What is happening is actually hydrocarbon absorption, where UV oxidation on TiO2 oxidize the hydrocarbon absorbed on the surface, and that makes the surface hydrophilic. if you leave it in the dark, there'll be natural absorption of airborne hydrocarbon, which make it hydrophobic. So same kind of mechanism we observed in the 2D materials, but operating on the oxide surface. It's quite interesting to say that people have been making the same kind of, I don't want to say mistake, but falling into the same trap again and again. This is a paper in 2013 from a group in MIT where they report hydrophobic ceramic material. Now that was a big deal at that time because in a lot of industrial applications, the heat exchanger would prefer a hydrophobic coating. Why that is? Because if you are dealing with condensation of water vapor, you prefer a hydrophobic interface because that creates water droplet condensation. So there's a difference between water condensed into droplets versus water vapor condensed into a water film. A hydrophilic surface will produce a water film-wise condensation, and that apparently reduces heat exchange. So you would rather to have droplet condensation so that water can be removed quickly. So when they discovered this hydrophobic ceramic material, which is a series of rare earth oxides, it was quite exciting because a lot of other hydrophobic materials are not thermally stable, but there seems to be thermally stable. However, if you think from a chemistry perspective, this is very counterintuitive because ceramic materials are highly polar. You have negative charged oxygen, positive charged metal ion. How could those be hydrophobic? It doesn't make any chemical sense. Now, when we look at this, we quickly realize that this is just another example of airborne hydrocarbon contamination. We repeat the experiment, making serum oxide thin film, and that indeed is hydrophobic, just as they reported. However, once you anneal the sample in air at high temperature, what we are actually doing here is we are burning off the surface hydrocarbon, and the films quickly become hydrophilic. So just another example of how the same kind of phenomena impacting different kinds of materials. And if you are not paying attention to the experiment and understand the chemical principle behind it, you may come to the wrong conclusion. So more recently, we showed that the same kind of process happens on gold surface. We prepared porous gold surface, and this is an optical microscope, and this is a scanning electron microscope. The intention there was to get a sense of what kind of hydrocarbon materials we're dealing with. And also, at the same time, the porous gold, as you may know, that they have a lot of interesting application in SERS, surface-enhanced Raman spectroscopy. This is a very popular analytical technique capable of detecting a single molecule in some cases. So there's a lot of interesting report within the search community about detecting single molecule, or what they claim to be a single molecule event. But when we look at those search substrates, in this case made of porous gold, we find that simply by exposing those surface material to air, produce search signal. And this is good in the sense that it gives us a way to characterize what kind of airborne hydrocarbons are there. So on the bottom, I show some of the representative images, Raman spectra we collected on those search substrate. You see some interesting features. For example, the black one, it's some kind of fine fingerprint feature related to long chain non-aromatic carboxylic acid. And there's also this broad feature around 1500, and those are usually related to amorphous carbon or large aromatic structure. And even in some cases, there's a feature around 2100 wave number. Anybody know what 2100 Web number corresponds to? It's a pretty unique IR signature. Anybody down organic chemistry? Yes? C, not CH2. CH2 is 2900. See, okay, that's pretty close. So carbon nitrogen triple bond is pretty close. This one is actually carbonyl, so carbon monoxide. And that is wild because I'm pretty sure my lab doesn't use carbon monoxide, and somehow we detect carbon monoxide absorbed onto on the search substrate. This is a XPS data again shows, hopefully you're familiar with this now, basically shows different kinds of carbon material being deposited on a gold surface. Again, by simply exposing a porous gold substrate to air, we start to collect hydrocarbon from air. And we see both carbon signal and oxygen signal. So again, this shows it's partially oxidized hydrocarbon material. Want to briefly show that we can detect search signal, and in this case, what you're looking at is a heat map, essentially the intensity of Raman signal, because this is search substrate. So this is we're just going to call it search signal, and so on the top, from top to bottom, we look at the same substrate, but we look at the same area after as a function of exposure time to air. So on the top is 1 day after the sample was prepared, we left in air, and then 3 days and 5 days. And what you see in the heat map is the appearance of those yellow dots. Now, yellow means higher Raman intensity. So what you see is as you increase the air exposure, you start to see a more and more stuff showing on the Raman, the search substrate. And those stuff are aromatic or non-aromatic hydrocarbons being accumulated on the surface and being detected by search because the search substrate enhances the Raman cross-section of the analyte molecules. On the right-hand side, I show the same kind of statistics, but just showing the relative intensity histogram, and you clearly see this high intensity part becomes more and more significant as you expose the substrate to air for a longer period of time. And so this one is aged in air, so we just leave the sample in air and didn't do anything special. Now the more interesting result is this one. This is very unexpected. So we did the same thing. We make a search substrate, we leave it in air for a couple of days, except in this case, we cover, so we put in a glass vial. So we have search substrate, we put in a glass vial, we leave the vial open and lay flat so air can go through. In this one, we cover everything with a glass filter paper. And surprisingly, now we do not see those Raman signature anymore. Okay. This is totally counterintuitive to us, and we do not understand fully what this means. But the data on the surface seems to suggest everything we saw, in this case at least, come from pretty large clusters. Could be amorphous carbon cluster, could be aromatic carbon cluster, could be aerosol, could be a lot of things, but it does not seem to be a molecular species diffusing in air. Okay. Again, we do not know whether this is specific to the metallic substrate case, or is it broadly applicable to all the cases we have studied. Now remember, in the case of graphite, we have done ellipsometry measurement where we see this progressive growth of thin film, and in that case, it seems to indicate it's the molecular species that is absorbed on the surface. But this one seems to be different. Okay, regardless, I hope that convinces you this is a very general phenomenon, and it happens on all kinds of surfaces. So chances are, regardless of what kind of carbon material, nanomaterial you're working with, there is some kind of contamination on the surface that just may be impossible to avoid. Okay, so you have to work with it. And from my perspective, the question is how we can understand it. First of all, whether this behavior have changed or modified some of the understanding we had about carbon material. And if it does, how much impact there is. And then last, but probably not, probably more important is, can we reduce the contamination? Can we get rid of the contamination? Are there any way we can improve material performance by understanding and manipulating the environmental factors? So those are the questions around the next, the rest of the talk. Okay, so I come back to this, this big application diagram. And so what we have done recently is to look at how the surface contamination would impact electrochemistry related application, and in particular energy storage, in particular very fundamental electrochemistry. And based on my introduction, there should be very significant impact because those processes all very closely involve some kind of interfacial process. So that's what we started. But before that, I also want to comment briefly on the concept wetting transparency. That's something a student asked yesterday, or maybe faculty member asked yesterday, so I felt I'm obligated to make a comment there. What you may recall is yesterday I showed two different wetting data. One is graphene on copper, another is graphite. If you think about graphite, you can view it as a single layer graphene on top of a graphite substrate. So you have two different substrates of graphene. One is a copper support, another is graphite support. If you look at the wettability data, after they got contaminated in air, their contact angles are water contact angle almost the same, 90 degrees. But before they were contaminated by air, the graphite contact angle is around 62 or 65, and the graphene on copper is around 45. So what that means is water droplet sitting on graphene, they can actually feel what is beneath graphene. And that idea is called wetting transparency. And the reason being, graphene is so thin, and the van der Waals interaction is long range. So water molecules sitting on top of graphene can feel, because graphene is only 0.3 nanometers thick, so whatever is beneath graphene can have an impact on the wettability data. This was a very powerful concept when it was developed in the early 2010-ish. But people have a lot of challenges identifying whether graphene was actually wetting transparent or not wetting transparent. Early studies concluded that it is completely wetting transparent, meaning that whatever the wettability of the substrate would dictate the wettability of the substrate with graphene coating. Later, a group in MIT saying, no, it's only partially wetting transparent. And then even later, another group in MIT in the same department published a paper saying that you're both wrong. Graphene is not wetting transparent. But once we look at our data, we realize that they're just looking at the same measurement, but do it in different ways, and as a result, they are looking at different degree of surface contamination. And once you take into consideration of the surface contamination, we come to the conclusion that the semi-wetting transparency theory is the most appropriate, even though in this case, their wetting data is actually also contaminated by surface hydrocarbon. Okay. So going back to electrochemistry, this is another interesting controversy, and you may notice I like controversies. So the subject involved here is the fundamental electrochemical activity of graphite. Okay. Graphite is a very good model system. Electrochemists like them for a lot of reasons. In part because graphite, if you think about the basal plane graphite, okay, I'm talking about non-functionalized graphite basal plane. That plane is chemically stable. It doesn't have any surface reconstruction. So whatever you exfoliate is what you get. You don't have to worry about chemical change. So electrochemists have been using this this basal plane graphite as electrode, model electrode for quite some time. And in the 1980s, there's quite a lot of research in understanding the fundamental electrochemical activity of basal plane graphite versus the edge. So the edge is the cross-section here. The difference between the two, as I said, the basal plane doesn't have any chemical functionalization, but the edge plane does because you break the carbon lattice, so there's a lot of oxygen functional group there. So back in the 1980s, a lot of work mostly done by McCurry, McCurry's group who was at Ohio State at that time. They did a lot of work showing that, demonstrating that the basal plane graphite is electrochemically inactive. And the edge plane is electrochemically very active. So at that time, it was understood that there's no specific absorption on the basal plane. And in addition, the electronic structure of graphite is such that the density of state is pretty low at the Fermi level. So that would support very sluggish charge transfer. So from both surface chemistry perspective and band structure consideration, people are happy with the conclusion. It makes sense. Okay. Except in early 2010, a group in the UK, Professor Patrick Owen, he's a very well-known electrochemist, doing a lot of interesting work in scanning electrochemical microscopy. He published a series of papers, and you look at the title, Definitive Evidence of Fast Electron Transfer at Pristine Basal Plane. So his study showed exactly the opposite conclusion from the early conclusions made by McCurry's lab. McCurry said the electron transfer in basal plane is poor, and Owen said it's fast. Okay. And they're both very well-known and very respected electrochemists in the community. In fact, McCurry, published a paper in Analytical Chemistry in 2012, after Owen published those, and you can imagine what they said here. So these two groups of people are studying the same kind of material, and they come to very different conclusions. Okay, not something uncommon in science, but given that both research groups are very well known and they know what they're doing basically, but still they come to a very different conclusion. So when we look at this, we realize that, oh, this is just another example of people working on some material, but they didn't know what they're getting, when they actually taking the measurement. They think they're using a certain material, but that may or may not be the case. So we take a look, and we realize that we just need to do cyclovatomogram. So if you recall the tutorial yesterday, what you do here is you scan the voltage and you collect the current. Okay, so what we did here is we have a piece of graphite and we exfoliate the top layer. So now we have a clean surface of graphite. And we use this surface, clean surface, as the electrode to collect cyclovatomogram. And we do this as a function of time, and this time is the amount of time we left the electrode in air. Okay. So this is done using iron hexcyanide redox couple. So this is one electron redox couple. And if you think about all the electrochemistry you have learned, the oxidation reduction peaks should be separated by 59 millivolt ideal, sorry, 57 or 59 millivolt ideally. So if the redox is reversible, that should be that would be the number you are expecting. And we are getting 60, so that's pretty close. Okay. And but we only get 60 if we do the measurement right away. So if we are doing the measurement within 2 hours, you see pretty significant, obvious oxidation reduction peaks in the CV. And that is a good indication that the redox reaction is reversible and fast. However, if you leave the electrode in air for much longer time, 6 hours, and especially after 3 days, you see 2 changes. One is the intensity of the current goes down. So the peak got reduced. Okay. But also the peak separation, the oxidation reduction peak separation increased. And both are classical indication of more sluggish, slower, or non-reversible electron transfer process. Now, how do I understand this? It becomes pretty obvious if you accept that the surface of electrodes are not clean after a couple of days. So if you have clean surface, there's no hydrocarbon, then the electron transfer would go directly from the graphite electrode to the solution redox couple. However, if you have a layer of oil, essentially, hydrocarbon, they are not conductive, then the electron transfer has to go through this additional layer. Now, this is electron tunneling, essentially, and the electron tunneling is exponentially sensitive to distance that you have to go through. Okay, so basically the hypothesis here is that interfacial contamination would reduce the electrochemical activity of basal plane graphite. Okay. Now, if you go back to this part and look at those very 2 different conclusions, you may guess that, in the case of Mercurius' work in the 1980s, they're probably working with contaminated graphite. And indeed, we think that is the case. We dig into their experimental section, and we found that they used a particular technique to define the surface area of their electrode. And the way they do that is to cover the surface they do not want to measure with paraffin oil. So indeed, they expose their surface with a lot of hydrocarbon to begin with, even though they do not cover all the surface with hydrocarbon. But the presence of paraffin oil would produce a vapor that potentially would contaminate all the surface, even though it doesn't look like that's the case from their perspective. Okay, so related to this, I'm going to talk about this briefly. How can we reduce the hydrocarbon contamination in the later part of the talk? But we figure out a way to slow down the contamination, and that is by covering the surface with water. And we can do this by simply exposing the electrode to low temperature. Again, more on this. But if you compare those 2 data, you find if we expose graphite to room temperature, we see this degradation pretty fast. But if we keep it at low temperature, and the intention here is to trigger a condensation of moisture on the surface, we can maintain the electrochemical activity pretty well, even after a day of exposure in air. So there's some hope of maintaining this, the electrochemical activity by very simple manipulation of environment. And on the right-hand side, I show this delta E, which is the separation between the oxidation reduction peaks a large delta E would corresponds to a lower activity in electrochemistry. And by storing at a lower temperature, we can maintain the delta E to values very close to reversible process. Okay. Now on to move one step further. I want to talk about contamination, not in air, but in aqueous solution. So what I show here are ellipsometry. You may remember I showed some of this in an earlier episode where we look at ellipsometry measurement of graphite exposed to air. Okay. Now here I'm doing the same kind of measurement, except I'm doing everything in water. Okay, so what the experiment is, I have graphite. I expose the graphite to some solution, aqueous solution. Okay. And then I have laser coming in, shooting at the liquid solid interface. And then I analyze the reflected laser light. By analyzing the polarization change and the intensity change, I can figure out how much additional thin film is being grown at the liquid-solid interface. So same experiment, except yesterday I was showing the growth of thin film at air-solid interface. Now I'm looking at the liquid-solid interface. So if you look at the diagram on the left, so there are 4 different traces of data collected, and they are measured in DI water or nanopure water. So this is supposedly the best water, the purest water you can get in the research lab. But still, in all the cases, we find accumulation of some material within about, I would say, 1 hour. And it plateaus at about half nanometer. So this is a very similar behavior we saw in the graphite in air kind of experiment, except in this case it's in water, and it's in the nanopure water, supposedly very clean water, but still you have this accumulation of some stuff on the surface. We repeated the same kind of experiment using an electrolyte solution. This is 1 molar of sodium chloride. And you see the same kind of accumulation of contamination, we think, on the surface, except this is much faster, first of all. And second, it goes all the way to about 2 nanometers over a long time. And if you look at this too, certainly there's additional sodium chloride. And we didn't use any ultra pure sodium chloride. We just get sodium chloride from Sigma Aldrich, and that's what we used. And clearly there's more dirty stuff in this solution compared to nanopure water. Okay, so I guess the point I want to make is, first of all, there is the possibility of maintaining the contamination layer can maintain structure in the aqueous solution. That's probably not entirely surprising, given that I already showed you that in the cyclovatomogram vattometry experiment, you do see the impact of this contamination. Okay. But regardless, in this case, the surface was clean to begin with. Okay. So your electrode will be contaminated by air and will be contaminated by water. It simply when that's going to happen. It's not about if, it's more about when. Okay, so with this in mind, we moved on and look at how this could potentially impact certain chemical energy storage applications. So in the energy storage application, in particular, we're looking at supercapacitor type of energy storage device. The capacitance of the material plays a very important role. Okay. Because the energy stored within the double layer structure. So the larger the capacitance, the higher the energy storage density you can achieve. Okay. So what we did here is on the left, we measure the double layer capacitance of graphite basal plane. And what we did is we exfoliate graphite, we leave it in air for a certain amount of time, and then we measure the double layer capacitance by EIS technique. Okay. And each data point on this corresponds to one separate exfoliation. So we did about 30 different exfoliations here. They are not on the same substrate, so there's a large fluctuation of data point. But overall, you still see this very obvious trend. That is, the longer you expose your electrode in air, okay, the more reduction of capacitance you will see. And you will see roughly 50% reduction if you leave your graphite electrode in air for about half day. Okay. All right. Again, I want to emphasize that this is on graphite basal plane, and this is on unfunctionalized graphite. And this is important because a lot of energy storage supercapacitors, they are not made of graphite. I emphasize this is a good model system, but it may or may not translate to actual device, okay? Because the surface contamination would be critically sensitive to the surface chemistry, and whether you have graphite or non-functionalized or functionalized, that can play a big role. Okay, but regardless, we see this reduction on the basal plane of graphite, and we see this whether the surface of the graphite is on top, face up or face down. It doesn't matter. So in this data set, it seems to suggest that it's not particle contamination, but rather molecular contamination. Okay. We also did the same kind of measurement, but by continuously measure the capacitance using EIS technique of the same electrode immersed in electrolyte solution. So what we find here is there's a rapid decline in the double layer capacitance within the first hour or two, and then it plateaus. Okay. In this case, we also tried some tricks to see if we can drive off the contamination. And what we did is we applied either a very positive or very negative potential. And we were thinking whether we can either electrochemically oxidize those material or maybe just repel them by electrostatic condition. And in both cases, we find quite some interesting recovery. So what we did is we do the measurement continuously, and then at here, we stopped the measurement. Instead, we apply minus 1.2 volt and hold it for some time, and then we resume the measurement. When we resume the measurement, we find, oh, we have some recovery. But then it got declined again. So it looks like we can get rid of some of those contaminants, but not 100%, obviously. And also, it goes back to the contaminated state pretty quickly as well. So some effect, but not very promising. So we later we continued this investigation, look at whether the same kind of contamination would impact a more relevant materials. By relevant, I mean the active carbon material that people actually use to make supercapacitor. Okay, so the difference being, again, the result here are done on graphite. Okay, graphite is a good model system, but nobody used graphite to make supercapacitor. Surface area just too small. What people actually use are active charcoal, active carbon, porous carbon material. Those are the ones actually being used in making supercap. Now those materials, they have very different surface chemistry. They have a lot of oxygen functional group because the way they are made. Okay, they're a lot more porous, so there's higher surface area. And we find those materials behave very differently. Okay. In particular, we expose the active carbon material to air for different amount of time, and we find there's actually no impact on the double layer capacitance when those materials are exposed to air in a lab setting. Okay, so that's good news. And what is happening here, we find, is because those materials are so hydrophilic, because they have a lot of oxygen functional group on their surface. They're very hydrophilic, so they got covered by water quickly if you expose to lab air. So the water actually protects them from being contaminated by hydrocarbon. Now, however, if you do everything by, if you expose them to a dry environment, which is, for example, a glove box, now we start to see this decline in the double layer capacitance, about 20%. So still pretty significant, but not 50%, and seems to be not an issue if you work with the aqueous electrolyte system. Okay. Now, the red data, which suggests this decline of performance in the dry environment, is also alarming because a lot of supercaps, they involve not aqueous redox, not aqueous electrolyte, but rather organic or ionic liquid kind of electrolyte. And in those cases, the surface contamination might be relevant. Okay. We also made model supercaps. We're not very good at doing this. But we made some very simple devices and look at how toluene vapor can impact the device performance. And here, there's no surprise. Exposing the device to toluene vapor, while exposing the carbon material to toluene vapor, greatly reduced the inner storage capability. And this is clearly shown in this charge and discharging curve. All right. Some additional work we have done is to look at electrical. This is not electrochemical, but now we look at electrical conductance. So why we're interested in this? Because a lot of MEMS, so microelectronic, micromechanical devices, they involve nanoscale electrical contact to operate. So we're interested in understanding how the electrical context at nanoscale could be impacted by a layer of hydrocarbon contamination. Now, in this context, conductive FM become very relevant. It's a highly popular analytical technique to analyze surface electrical conductance. And in the context of conductive FM, it is very well known that the liquid bridge can significantly impact the conductivity measurement in CFM imaging. So the basic idea there is any surface you expose to air, people know and understand that there's a layer of water. Okay. So pretty much all surface you work with in air, you should assume there's a layer of water. What people never thought about before was there should be a layer of hydrocarbon as well. And within the conductive FM community, people know this model, this water meniscus model, and knowing that if you have AFM tip, so this hemisphere is the tip of AFM probe. Okay. It comes down to the surface, and then that structure, this contact would create a capillary condensation effect to accumulate water. And that water would change the local conductivity behavior, and that could increase the current measured in a CFM experiment. And what we showed recently was that this layer of organic contamination actually produces the same kind of effect. So you would see this modulation of electrical current in the presence of hydrocarbon contamination, even if you are working in a dry environment. To illustrate that case, I show a bunch of, so this is a bunch of current voltage curves. So what we did here, again, is we have this AFM tip. I'm going to use this. So AFM tip, and this is my graphite substrate. And we push the tip to the surface. And when there's a contact, we apply voltage between the tip and the substrate, and then we measure the current. Very easy. So we do this in different environment. In one case, we look at we look at freshly exfoliated, and what we find is if you apply even a very small voltage, the current quickly saturates. So that means the electrical contact is very good. Okay. But once you age the graphite in air for longer and longer period of time, 5, 7, and 9 days, you start to see this reduction in the current. You apply voltage, the current doesn't go to saturation as fast, and instead you see this gradual, this nonlinear IV curve. Okay? And there's some indication that if you do the measurement repeatedly, there seems to be a way to drive off those hydrocarbon within the tip. Okay. We also did experiments which I didn't show here. We look at the conductivity in a dry and a clean environment versus a dry and a dirty environment, and then a wet and a clean environment and a wet and dirty environment. And we were able to show that in this case, you get the least electrical conductance, the least electrical conductance, because there's no meniscus established between the tip and the substrate. And in both those cases, you can see an enhancement in the electrical conductance, okay, compared to this one. All right, so in the last part, I want to talk about cleaning. And that was one of the questions from yesterday. We already know that there's this extensive surface contamination, and it seems to be unavoidable in air. So if you want to get a clean surface, and there seems to be a lot of benefit of getting a clean surface, the electrochemical activity seems to be a little bit higher, and in addition, the double layer capacitance seems to be a little bit higher. So would there be a possible outcome in maintaining the surface to be clean, or to prevent the surface to be contaminated in the first place? So after our work, and in parallel to our earlier work published on surface contamination, a lot of people have looked at ways to clean the surface. At least some of them, we showed, for example, that if you have a dirty graphite and you just simply expose it to high vacuum, ultra high vacuum environment, some of those contamination actually automatically desorb under high vacuum environment. And the example we did here, for example, is to put a dirty graphite sample to an XPS chamber overnight. We take it out the next day and find the water content actually reduced from 80 to 65-ish. So some kind of evidence of desorption of hydrocarbon. But this is not very, meaningful if you are, it's meaningful if you work on a small piece of sample doing research, not meaningful if this is related to industrial fabrication. We also showed that if you apply high temperature, that helps to drive off the hydrocarbon. Again, it's working, but only to limited extent. There seems to be some remaining hydrocarbon that cannot be driven off. There are other people look at very innovative approaches. This one is quite interesting. This is CO2 blast. So was actually a dry ice. So what they did is they start with high pressure carbon dioxide, and they release the pressure that the non-adiabatic cooling produce dry ice because of the cooling effect of rapid expansion of gas, and that produces a lot of small dry ice particle. If you blast that stream of dry ice particle to surface, it carries the surface contamination away. Now, what's so beautiful about this is dry ice particle will evaporate into CO2, so you are not going to leave any residue. So in a sense, you can wash the surface, but you are not leaving any additional contamination from the solvent. Okay. So this works in, I think quite beautifully, but also you're blasting the surface with some solid particle. You could damage the surface, and also this is a pretty expensive process. And then some people try so-called dry cleaning. Basically means they add some other sorbent to capture the hydrocarbon. That seems to work in some limited cases as well. And of course, there are chemical ways you can oxidize the surface. And how they showed, in the case of TiO2 and in case of ceramic material, you can simply apply a high temperature, and that would, drive off this, the hydrocarbon pretty easily. We showed that, as I mentioned earlier, simply by covering the surface with water, we can prevent the hydrocarbon absorption. And the evidence seems to suggest that you can form a monolayer amount of water on graphite surface. And this is quite surprising to us. And it appears that once you have this monolayer amount of water, the hydrocarbon is less likely to stick to the surface. We think they probably still absorb to the surface, but because a lot of the applications we're interested in particular electrochemistry, would involve working in the aqueous environment anyway, it seems that the interaction becomes more, it's a little bit easier to release those hydrocarbon contaminant. At least that's the kind of model we're thinking. So this shows you the evolution of the water contango as a function of time. And you may notice that, so the black is graphite. Okay, so graphite, we do exfoliation, and the first data point is around 65, as you may recall. So this is the black curve. And very rapidly, the contango of graphite increased to about 90 degrees. You may recall this same kind of behavior I showed yesterday. And then, plateaus around 90 degrees. So classical behavior that I already showed. Now, if I leave the graphite, if I do the exfoliation of graphite and I immediately put into dry ice temperature, I just store it around a bunch of dry ice. And then you take it out periodically to do the contango measurement. Surprisingly, you find in this case, the contango doesn't increase as fast. Instead, it simply fluctuates between 60 and 70. So it doesn't increase anymore. We also look at an experiment where we store it at low temperature, and then we move it to room temperature, and quickly we see this increase in the water contango. So it seems to suggest that low temperature storage would slow down the absorption of hydrocarbon and make the surface more remain in hydrophilic state for a much longer period of time. We confirmed this, this is not a temperature issue, but rather humidity issue. And this can be shown by looking at the desiccant effect, meaning that if we expose the graphite to a dry environment, the contamination seems to be faster. And also another control where we're not going to do low temperature experiment, but instead we simply expose the graphite to high humidity. And this high humidity can be created by exposing it to steam, so 100% humidity. And in this case, you find that the high humidity environment also protects the surface of graphite, within 120 minutes. There's no increase of contango to 90 degrees. And in the control experiment, we expose the steam to air-aged graphite. We find the surface remain hydrophobic. And this indicates that steam doesn't damage the surface. It's not a chemical damage that makes the surface hydrophilic, but rather is something intrinsic about the relative humidity of the environment that keeps the surface in a relatively pristine state. Later we also did measurement using FTIR technique and showing that there is actually a very strong indication of hydrogen bonded water network on the surface. And even more surprisingly, this hydrogen bonded water network seems to be stable. So once they are formed, this seems to be stable even in much lower relative humidity, and suggesting that there seems to be a lot of hysteresis of formation and disruption of the hydrogen bonded water network. So we still don't know a lot of the details, but regardless of the mechanism, if you recall the electrochemistry data I showed before, by keeping the graphite in a low temperature environment, we can keep them electrochemically active after even 1 day. So that was quite impressive in our own assessment. So I probably have about 10 minutes, and I'll quickly talk about another groups of application where we look at how another environmental factor can impact performance of carbon materials, and this would be a mechanical strain. And I want to talk about 2 different examples. And in one case, I want to show how mechanical strain, either tensile or compressive, can impact the electrochemical activity of graphene. And in another case, how they can impact the chemical activity of graphene. So in this set of experiments, what we did is we make chemical vapor deposition grown graphene. We put them onto a polymer substrate. This is essentially a piece of plastic. What we can do then is we can bend them in different ways. And depending on the direction of the bending, okay, we have, well, a piece of plastic, we can bend it in this way or in this way. Right? Depending on the direction, we can create a tensile strain or compressive strain. Okay. And what we are doing at the microscopic level is we're simply compressing the carbon-carbon bond, okay, or elongating the carbon-carbon bond. Now, if you look at the Raman data here, you can see what we are focusing on is the 2D peak. As I mentioned yesterday, the 2D peak is sensitive to a lot of environmental factors, and strain being one of them. If you apply strain depending on the direction, you can systematically shift this peak in both directions. A compressive strain would shift in one direction and the tensile strain in a different direction. And people have produced calibration curves. So based on this shift or Raman peak, we can figure out in percentage-wise how much strain we are impacting onto the graphene thin film. Then what we did is we bended in different direction, and then we used this graphene substrate as electrode, and we do a hydrogen evolution reaction on this electrode. So this is the data. What we did essentially is we altering the strain as a function of time. So if you look at this one, okay, so the strain is 0, and then we apply positive and then come back to 0, and then after some time we apply even greater strain and then come back to 0. So we essentially we're doing this bending or not bending, bending, not bending, a different amount of bending, and the amount of bending would create different kind of strain. This is the raw data. The data, the electrochemical current decays over time, probably because of surface contamination. I don't know exactly what. But on top of that, when we apply the strain, we see this periodic drift. So if we get rid of the background, we got something like this, which is more easier to analyze. So what you see here is when we apply strain, we find this enhancement of electrochemical current. And when we release the strain, it reverses back. Okay. And overall, we see this very positive correlation between the amount of strain and the kind of current modulation we see in the electrochemistry. To understand this, the model we use is thinking about the hydrogen reduction process, and a key step there is the absorption of hydrogen atom being a critical intermediate step. So what you have here is a model where we have graphene surface, and the model we have is the hydrogen atom would absorb onto the surface, interacting with one of the carbon atoms. And this absorption energy would be, well, the absorption of hydrogen atom to the surface would lower the energy of the hydrogen atom. So this is a known mechanism called hydrogen evolution reaction. And a stronger absorption would essentially lower the activation barrier. Okay? But you can't make it too low. If you make it too low, then you are trapped with the intermediate. Okay? So what we're doing here is essentially we're modulating the absorption energy as a function of the lattice parameter. So when we bend the graphene, we're essentially changing the carbon-carbon bond. And you may imagine that if I weaken the carbon-carbon bond, make it easier to absorb the hydrogen atom. Okay, I don't know why the other part is missing, but we also did another experiment where we look at the modulation of chemical activity, essentially oxidation of graphene as a function of environmental factors. But I'll skip that, I guess. So I guess in conclusion, I hope I convinced you that a lot of properties, not limited to wettability, I would say a lot of properties in general are likely affected by environmental factors. And certainly graphitic surfaces are more hydrophilic than what people used to think. They are not super hydrophilic, but they are more hydrophilic. Okay? And we see the same kind of impact of environmental hydrocarbon absorption on electrochemical, fundamental electron transfer rate constant, and also on double layer capacitance. And we show the same kind of effect seems to impact model supercapacitors. And there seems to be ways we can slow down, but probably not to completely reverse the absorption. In the electrochemical setup I showed you, there seems to be some temporary restoration of surface cleanness, but again, not a permanent solution. So I'm a little bit pessimistic at this time, but the bottom line, I think the silver lining is at least we know this is happening, so we can actively think about how to minimize its impact to the measurement, to our study and understanding of the surface properties. So I'll stop here. We'll have 20 minutes to discuss more questions. Okay. Thank you.
Thank you so much, sir, for your illuminating lecture on interfacial properties of carbon nanomaterial. Can I have the questions from audience? Yes. Aditi, mic. Can you be a bit louder? Can you be a bit louder? Yes.
In one recent paper, I read that carbon quantum dots are made by laser image. Can we make it from other type waste material also? In in one paper of RSC, In one research paper,
Hello. Hello.
So the question, yeah. So the question is about the production of carbon quantum dot, and there are reports of making carbon quantum dot using waste material. I think that's what you're asking. And the question is, are there other ways of or different sources of making carbon quantum dot? Is that the question?
Is that the question?
Yeah. So yes. So right. Yeah. So indeed, there's a wide variety of reports on manufacturing of fabrication of carbon quantum dots. Usually, this involves some organic compound. Can be a waste material in some cases, and this often involves some kind of high temperature process or digestive process, hydrothermal process, and the approach is also very wide ranging. And the end result is some kind of fluorescent material, and the biggest concern when I read this paper is the characterization, because there are so many different things that can happen during the hydrothermal processing of organic compounds. There are condensation of small molecules that can produce aromatic compounds, which can be fluorescent. There's certainly condensation and the dehydration of compounds that can produce amorphous carbon or even carbon cluster. Those are all possibilities. The challenge is how to properly characterize those. And the more the one paper I come to my mind is the solid state and MR, solid state MR and solution MR analysis of one of those approaches, in which case they find a specific organic molecule is responsible for the fluorescence. And that just changed a lot of my perspective. So a lot of those applications, they make carbon quantum dot for sensing application. I think, whatever sensing application they do are still valid. It's just the interpretation of where the signal come from and what is the actual material basis of the optical property that needs to be more critically assessed. I still don't know whether it's a one-time, reproducibility issue, or maybe that small molecule actually applies to all the materials people have been using in making carbon quantum dots. Because, as you said, carbon quantum dots can be made from such a variety of different materials. So the actual mechanism might be very different depending on what kind of material you're using. Maybe in some cases, people are actually getting carbon cluster. Maybe in some other cases, it's a condensed organic molecule. I don't know the answer to all of them. But you probably see the theme of a lot of my talk is about controversy. So I like to follow on this.
Hydrogen storage. Can we use such type of material for hydrogen storage?
For carbon quantum dots? So the question is about possibility of using carbon quantum dots for hydrogen storage. I am not expert in hydrogen storage, but my sense is carbon nanomaterial would have limited potential there, especially carbon quantum dots in particular, because there's a limited chemical mechanism to absorb hydrogen gas. Typically, those involve some kind of chemical transformation. But nowadays, it looks like simply doing a high pressure cylinder storage that might be commercially viable. I mean, there's already hydrogen-driven car, and those are done entirely by using the cylinder of hydrogen. A lot of people using MOF and many other things, but I think carbon quantum dot structure might be challenging to produce hydrogen storage application. But that's just my limited view.
So
Yeah. So the question, the question is how can we protect the surface from hydrocarbon? And I do not have a good answer for that. The water is one approach we tested. It worked to some degree, but we're talking about a day and not a year, right? In the context of electrochemistry, this is nothing new because electrochemists are very aware of surface contamination, especially under electrodes. It is a standard practice, my understanding is when people polish their electrode, when they're done, they always put in water. And that has some benefits, especially if you are working with a hydrophilic electrode. There is, once you wet the surface, then hydrophobic materials would be less likely to cover the surface if your surface is hydrophilic. Now, graphite is a bit special in that its wettability is not that hydrophilic. So you see this surface contamination even if you are in water, simply because the wettability, the water content is around 60 degrees. But things will be completely different if you are working with a superhydrophilic surface. In that case, the hydrocarbon contamination is going to be much slower. We also see this in solid surfaces. As I said, this contamination would happen on pretty much everything. You expose anything to air, hydrocarbon eventually will absorb onto the surface. But if you compare the case of silicon oxide, which is hydrophilic, versus graphite, which is much more hydrophobic, contamination on silicon oxide is much, much slower. Contamination on graphite happens within 10 minutes to an hour. The same thing will happen on silicon wafer, silicon oxide glass, but on those cases, it happens over weeks, days to weeks. So the difference in the kinetics is, 10 or even 100 times slower. And one reason for that is, in my view, is because the glass and silicon oxide surface is much more hydrophilic. So there's a significant kinetic barrier for hydrocarbon to stick. Now, thermodynamically speaking, hydrocarbon will always win because a lot of the hydrocarbons we're talking about, we think they're high molecular weight hydrocarbon. Water is small, water molecule is low, so if you think about the absorption process, you have enthalpy contribution, you have entropic loss. So the translational loss of entropy is more or less the same, whether it's a large molecule or small molecule, because a lot of it is the translational entropy. So eventually, if you have a large enough molecule, the enthalpy contribution will dominate, and the enthalpy interaction would scale with molecular weight if you are talking about van der Waals interaction, and so large hydrocarbon will eventually win. So just like oil, will eventually wet the surface, and your glassware in the in the lab, eventually they all become oily. Your car window will eventually become, dirty if you don't wash them, even though
Hello.
they are pretty hydrophilic to begin with.
Hello.
Good afternoon. Sir, how can we आवाज नहीं आ रही
So this question is about control of purity and the uniformity of carbon nanotube and graphene during large-scale production. This is a very good question. I'll break it down into different parts. On the carbon nanotube side, there's a lot of work done on the growth of single-wall carbon nanotube. And in some cases, you can grow nanotube into specific chirality. So when I say chirality, you think about the rolling direction. As I said, you can roll into different direction from a graphene sheet. So if you pick the right catalyst, and it doesn't work in every case, but in some cases, if you pick the right catalyst, you will get a particular kind of carbon nanotube. It could be metallic, it could be semiconducting. Okay. So that is done in some cases. Now, there's also a lot of work done in terms of purification of carbon nanotube. So maybe you're growing carbon nanotube, they grow into a mixture of metallic and semiconducting. Now, once you have this mixture, because of the graphene sheets are wrapped in different way, okay, there are actually ways to sort them into different, just like you run a chromatography of organic reaction mixture, you can do the same kind of purification of carbon nanotubes based on their structure. One such approach is to wrap carbon nanotube with DNA. You can find a particular DNA sequence that recognize certain kind of carbon nanotube. And by doing that, you can separate carbon nanotube into specific chirality. This is a very surprising outcome, but that has been very extensively researched. So that's on carbon nanotube. And for graphene, there's not a lot can be done for the exfoliation process. There's some control you can have. You do exfoliation, you get different layer thickness. You can, for example, do centrifugation, and you can separate the batch roughly by layer thickness or by size, but that's not a very good control. For electronic, nanoelectronics related application, there's a lot of promise in the growth of single crystal graphene, where you can start with a single crystalline sheet of copper foil. And it sounds like a very fancy substrate, but it's actually very easy to make. You can simply heat up copper foil, polycrystalline copper foil, and let it do directional cooling. And whatever nucleate at the very beginning will propagate, that nuclei will propagate, and you can end up with a single crystal copper thin foil. And from there, you can grow single crystalline graphene. And people also done row-to-row production. You have a row of copper foil. You can do the rolling and do the graphene growth at the same time. So that has been demonstrated as well. So there you can have some control over the quality of graphene, crystalline graphic direction. And also, on top of that, there are also work done to control the layer thickness, whether it's single layer or two layer, and that can be done as well. The question is about how do you compare the properties of single wall carbon nanotube or multi-wall carbon nanotube? How do you assess, I guess, a metric of each other? Yes. Okay. So that's a very good question. Now this multi-walled carbon nanotubes, because of their complexity in the structure, it's very difficult to get a high purity of sample. Now, a lot of those materials, they have a very good application in as a mechanical enhancement filler, for example, as a in general a conductive material, as a electrical catalyst. Those kind of applications, you don't really care what kind of chirality you have, as long as it's conductive, is fine. The single-walled ones, they have much more defined properties, especially optical and electrical properties. If you're gonna make transistor device, you want strictly semiconducting single-wall carbon nanotubes, and the semiconducting tubes are always going to be single-walled. If you have multi-walled, the chance of getting every shell being semiconducting is very low. So for the multi-wall tubes, they are probably almost always going to be metallic, because if you have a mixture of metallic and semiconducting, the metallic behavior will dominate. So for nanoelectronics, I think the single-walled tubes are going to be desirable. For a lot of optical applications, medical applications, for medical imaging, oftentimes you require a near IR emitting fluorophore, and the single-wall carbon nanotube can be useful in those contexts as well. So basically, if you want some kind of optical, electrical application, chances are you want single-wall tube. For mechanical reinforcement, electrochemical, I would say you don't really. I think you do not care too much about the nature of the tube. So that's my feeling. Yeah. Okay, so the question is, how does the humidity impact the performance of graphene oxide sensor? This is something, this is a bit more specific. I'm not expert in the sensing. Now I can comment on that in some very generic terms. So if you are talking about gas phase sensor, then it will involve several important steps. One of them being the diffusion of the gas molecule to the surface, and some kind of interaction between the surface and the sensing material. So talking about signal transduction process. Having the relative humidity would impact all of them. In particular, there should be a competition. One would expect a competition of surface absorption, whether it's water or your analyte. And that can be important depending on what kind of sensing mechanism you're working with. I would expect some kind of reduction of sensing sensitivity in a high humidity environment. But again, that's a very generic, speculation. Yeah, but again, I don't want to pretend I understand everything, especially on the sensor side. Yeah.
Hello, hello. What type of contaminants are tolerated in supercap? Hello. What type of contaminants are tolerated in water-based supercap and how these affect electrochemical stability? So you told about water-based supercap and non-water-based supercap.
I think you're asking what kind of contaminants are tolerated?
Yes, sir, yes, sir. What type of contaminants?
Okay, very good question. We actually have no idea. Uh, okay, so something, so remember at the beginning of the, so in this SIRS study, we're actually very interested in figuring out what kind of contaminants are there. Unfortunately, that just made everything more complicated because the data seems to suggest the behavior on the SIRS substrate is different from the carbon material. But in this case, at least we find a couple of things that are relevant. Okay, let me see. Pointer. Okay, so for example, this is some kind of branch chain structure, carbon chain. And this one is related to some kind of carbonyl structure that's, and this one is, as I said, is the carbon monoxide. And this seems to be some kind of thermal decomposition product coming from the contaminant. Now in the ellipsometry measurement where we showed the buildup of the contamination layer, ellipsometry unfortunately doesn't provide any chemical information. All the modeling is made of assumption of certain refractive index. So we cannot know for sure exactly what kind of contaminant is there. Now, what can be done, I think, is some kind of mass spectrometry technique. Atmospheric ionization mass spectrometry technique. And this is something I'm trying to develop a collaboration with another colleague where we're going to look at graphite surface and we do atmospheric ionization and coupled with mass spectrometry, I hope we'll be able to directly detect what is on the surface. Our assumption right now is that this is some kind of long chain high molecular weight hydrocarbon. For the aqueous chemistry, the high molecular weight species would not be tolerated. Instead, the low molecular weight species are probably fine. The more polar compounds are probably fine. It's all about surface absorption energy in my view.
Okay, thank you, sir. So one more question is that, you told us the way of graphene clean synthesis of graphene. So which method we can clean the graphene when we synthesis from the CVD method?
I think you asked about CVD synthesis of graphene, but I didn't catch the question.
So graphene synthesis from CVD. So which method we can use for cleaning purpose? Which method?
Which method is better for graphene synthesis?
Yes, yes.
She's asking which method is better for graphene synthesis, either CVD or how much choices that we have.
Oh, so the question is what method is good for graphene synthesis? Right. So again, because the wide variety of synthetic approaches, cleaning? Oh, what cleaning process? Oh, okay. So what cleaning process are suitable for CVD graphene? Okay. Yeah. So there's so the cup of cleaning process I showed. I think the CO2 blast would work in some cases if the graphene is deposited on the mechanically strong substrate. And that's because if the graphene substrate interaction is not strong enough, then the graphene would risk being damaged by the CO2 blast. The UV ozone technique can be tricky because the UV ozone can oxidize the hydrocarbon very easily, but also can also damage the lattice. So you have to control the degree of oxidation carefully. But UV ozone can be amenable to large area processing. The only other thing is the high temperature annealing. You can do this at about 300, 400 degrees Celsius. You won't damage CVD graphene at that temperature. And you can apply reduced pressure at the same time. So depending on your requirement, but none of them will work perfectly. I'm a bit more pessimistic on that side, but on the other hand, if you can figure out a way to clean them very well, that can be a very impactful discovery.
So my question is, what are the factors that affect and contribute to the transition of inactive to active behavior in basal plane graphite?
I didn't.
Like factors that affect or contribute to the transition of basal plane graphite. Basal plane graphite.
Basal plane.
Once more, what are the factors that affect or contribute to the transition of inactive to active behavior in basal plane graphite?
Okay, so the question is what factors impact the transition of from inactive to active of the basal plane behavior? Yeah. I speculate you're talking about the electrochemistry?
Yes, sir.
Okay. So there's, as I said, there's this very different outcome in the electrochemical measurement. And from our view, whatever has been reported for the inactive behavior, they are due to surface contamination. Now, this transition would be, in my view, from active to inactive. So active is the intrinsic behavior. Inactive would be the extrinsic behavior. So if you have a clean surface, it would naturally be a highly active electrode. We have a collaboration with Shigeru and Mimia's lab showing that if you keep the surface of graphite and graphene clean, the electron transfer rate constant on those surfaces can match that of platinum and silicon and the gold. So it can, approach the metallic, ideal metallic behavior electrode. So those should be the intrinsic behavior of the basal plane electrode in my view. And whatever contamination on the surface would render the surface less desirable.
Hello. Sir, my question is, how if we have prepared graphene oxide and the presence of oxygen containing groups in graphene oxide, how it can improve the interaction of the enzymes in biosensing?
How, I think you're talking about how you can increase the activity of enzyme?
Yes, how it is interacting with the enzyme and how it can improve its interaction with the enzyme when we are using it in application in biosensing.
Well, I'm not very familiar with that particular application, but I think for very generically speaking, if you have enzyme coupled to carbon materials in general, I know a major consideration, one is the surface accessibility, obviously, but also potential denaturing factors. because those processes would require a lot of chemical processing and subject the enzyme to a new environment. Now, the carbon surface is much more hydrophobic, even though it's more hydrophilic than people thought, but overall it's still a more hydrophobic environment. It could trigger a denaturing of a lot of enzymes. And that can be managed by some surface passivation technique. You know, if you modify the surface with PEG or zwitter ion complexes or polymers, that may reduce the denaturing tendency to some degree. Other than that, I don't really have any other first-hand experience to share.
Okay, sir. Thank you, sir.
A question?
We can have questions from previous lecture also. Anyone is having any questions from previous lecture? We have a question. The person is asking how the CNT speed up the process of etching, and is this CNT based etching method useful only for silicon wafer, or it can be applied to other materials too?
So there's a question from online audience asking, explain the simple terms how the CNT helps speed up or guide the etching, and whether this is something that's useful for other materials. Thank you. So this is a very good question. In fact, it's a very generally applicable approach, and this is actually something I will talk about on Friday. So the general principle there is, again, you have this unique chemistry process where HF etches silicon oxide, and this reaction can be catalyzed by water. So, okay, this is done in gas phase, so you have HF vapor coming in, reacting of silicon oxide surface. It produces water, but the reaction itself can be catalyzed by water. So if you think about the overall process, when you have a silicon oxide surface, there's always some water absorbed on the surface. And that surface of absorbed water would catalyze the surface etching process. If you have a way to trap the water on the surface or to locally increase the concentration of water on the surface, then locally the etching of silicon oxide would be faster in those areas. Now, simply by having, carbon nanotubes, it might not be the best example, but think about a single-strand DNA. Okay, imagine you have a single-strand DNA sitting on a silicon wafer that has an oxide top layer. The presence of that DNA strand would increase the concentration of water around itself, because DNA is much more polar compared to an area that does not have DNA. So the single-wall carbon nanotube would do the same thing, but essentially increase or trap water on a very local basis, and that makes the reaction happening a little bit faster. The etching will be faster around the DNA and around the single-wall carbon nanotube. It actually happens in the case of graphene as well. It happens in the case of protein as well. So if you put anything that can trap water, that can absorb water on silicon oxide, you can increase the etching rate locally. Essentially, you can imprint the shape of silicon oxide. So we have in broad range of nanostructure template, in carbon nanotube, in even residue work the same way. Very generic behavior. Okay, I think you're asking for how to property of graphene? Oh, surface of graphene. Yeah, I think the question is how do we manipulate the surface of graphene to improve interaction with polymer matrix? That again is a very good question, and it relates to the broad of composite materials. Very generic response would be some kind of surface modification that can in the going back to the era of carbon fiber, know that you have to activate the surface fiber so that they can have good now one approach could be creating surface functionality fiber and couple that functionality with the function group in the polymer. Covalent connection that in my can be the strongest. Now may or may not be the best the mechanical performance. Sometimes less is more. Composite, the mechanical behavior be directly translated or scale one. If you have too rigid attachment, you may break each one of them. But if you have more flexible attachment, and if you have to break them all together, it's difficult. So that there has to be some kind of compromise in the bonding and the topology. Both are important. But if you simply are concerned about interaction, I think the generic approach would be some kind of activation. If you make it more hydrophilic or make the surface energy higher, overall the interaction will be stronger. Thank you.